Hello, and welcome to the third video in this series. I'm going to go over the outlines and objectives again. So in video 2, which was the last video, it was all about spectral phase. So we used the wave representation we introduced in video 1 to kind of explain spectral phase. We explained that you can separate the phase into all of its orders or its components. And then we talked about how if we manipulate one of those components, what does it do to the pulse? So we talked about 0th order phase, 1st and 2nd order phase. And so we talked about how 0th order phase shifts the phase of the waves within the envelope. So it's kind of the absolute phase. We talked about how that's much more important for shorter pulses rather than larger pulses. It has a more pronounced effect. We talked about 1st order phase, which shifts the pulse in time, and it shifts it differently. So if you do the Taylor series with respect to 0, and we do a 1st order phase shift, it'll shift the pulse in time. But if you do a Taylor series with respect to omega naught, and you do a 1st order phase, it'll shift the envelope of the pulse in time. So we mentioned that. And then we talked about chirp, which is the 2nd order phase. It stretches the pulse in time, and it causes a frequency dependence. So it starts at a high frequency and goes to a lower frequency by the end of the pulse, or vice versa. And so we used the wave representation to kind of intuitively explain why these changes leads to those effects. But in this video, which is video 3, I want to talk about the intensity spectrum. So why does a broader bandwidth lead to shorter pulses, and why does a shorter central wavelength lead to shorter pulses? And so I want to kind of use the wave representation again to kind of explain that. So first, some sort of nice little pictures to look at. So here's for bandwidth dependence. So why does a broader bandwidth lead to shorter pulses? And here's a nice little graph that kind of shows this. So here on the left is the intensity spectrum. So we have the x-axis is wavelength and the y-axis is intensity. And on the right is the pulse in time, the electric field of the pulse in time. And so as you can see, we're growing the bandwidth, the full width half max of this intensity spectrum. We're including more and more wavelengths. And as we do that, the pulse is shrinking in time. So a broader bandwidth leads to shorter pulses. And so the question is, why is this? Why does including more and more wavelengths lead to a shorter pulse? So I'm going to use the wave representation to explain this. So if you do the GIF of the wave representation that we introduced in video 1, it looks like this. So here's the pulse in time, and here's the wave representation. And so you're going to see as we're growing the bandwidth, we're including more and more wavelengths. They're adding up, the ridges are getting longer and longer, and you're getting this cancellation, and it leads to a shorter pulse. And again, I just want to mention, I talked about this a lot in video 1, but just to mention again, this encodes the intensity spectrum. If you plot the intensity spectrum here, it matches 1-to-1 with this. This actually encodes the area of waviness corresponds to intensity on the intensity spectrum. But how can you explain why does a broader bandwidth lead to shorter pulses? Well, I have to take 2 snapshots to I can't really talk over a GIF. So here's 2 snapshots. One is a narrow bandwidth, and one is a broad bandwidth, and the top are the resulting pulses. So for a narrow bandwidth, an analogy is kind of useful here. If you had an 800 nanometer wave, let's say, and an 800.0001 nanometer wave, and you line them up, they have very similar wavelengths, obviously. So the question is, how far would you have to go out until the peak of one wave aligns with the trough of the other? If you had these 2 waves, well, you'd have to go out very far because it's 800 and 800.0001 nanometer wave, right? They're going to look like the same wave for a very, very long time. And you have to go very, very far out until you get the point at which the peak of one aligns with the trough of the other. And that's sort of the argument here. When you have a narrow bandwidth, all of the waves that are significantly contributing to your pulse, which are mostly these, right? These top and bottom ones contribute it's a Gaussian spectrum, so very small, but the main contributors are in a very small wavelength range. And so they look like the same wave for a very, very long time. So the question is, how far would you have to go out before the peaks align with the troughs and you get cancellation? Because that's where the pulse ends. That's when the pulse gets decreased in intensity significantly. And if you draw that line down, it's roughly here. See, the peak in the very middle is aligning with the troughs at the top and the bottom, and that corresponds to a very low amplitude pulse. And so you'd have to go out this far until you get the peaks aligning with the troughs. But for a broad bandwidth, what does it look like? So for a broad bandwidth, you have very different waves. You're including a lot of different wavelengths and frequencies adding up to make the pulse. And so going back to my analogy, if you had an 800 nanometer wave and a 400 nanometer wave, how far would you have to go out before the peaks align with troughs? Only one wavelength, right? So that's sort of the argument here. You don't only have to go out this far until the peaks align with the troughs because you have very different waves, right? You have a very different set from your central. And you get cancellations not that far out, right? So the pulse will cancel earlier in time because the wavelengths, fall out of phase earlier in time because they're very different in wavelength. That's sort of the argument here. So let's talk about central. That's why a broader bandwidth leads to shorter pulses, but why does a shorter central wavelength lead to shorter pulses? And so we can do the same thing here. I have a nice little GIF to show this. So I have an intensity spectrum here with a constant width, but I'm just translating that across from 1,000 nanometers to 300 nanometers. And here is the resulting pulse in time. So you can see as you're shifting to shorter wavelengths, so a shorter wavelength leads to a shorter pulse in time. So why is this? And again, I'm going to plot the wave representation of this to kind of explain this. And if you do that, you get this. Right? Remember, because this axis is wavelength, it makes sense that you're shifting from long wavelength to short wavelength. And here's the resulting pulse in time. It's clearly shrinking. And again, this encodes the intensity spectrum. If you plot the intensity spectrum next to it, it follows 1-to-1. But again, I have to take 2 snapshots because I can't talk over a GIF. So here are 2 snapshots, one centered at 600 nanometers and one centered at 1,000 nanometers. So for this argument, we can't really use the same thing of like, oh, they're this different in wavelength, so they look like the same wave, just like we did for the bandwidth, because we know the area of waviness is the same, right? We kept the full width half max the same, but it's just the central wavelength that's shifting. And so why is it? So, I mean, let's use our thinking caps here. What do you see that's different between these two? Obviously, I mean, sure, this one's lower here, but that's only because the y-axis is wavelength. But what you see is that there's many, many more waves here than here, right? And why is that? Because this wavelength is 600 nanometers. So you can fit more waves in the same amount of time than this one. And that actually becomes the argument. If you have to go out, let's say, what is it, roughly 7 wavelengths out before you get the point at which peaks align with the troughs and you cancel out the pulse, then 7 wavelengths out of 600 nanometers is going to be shorter in time than 7 wavelengths out of 1,000 nanometers. And that's sort of the argument, is that you can fit more waves in the same amount of time. Sure, you only have to go out 7 wavelengths, let's say, before you get the peaks aligning with the troughs for this wavelength range. But 7 wavelengths out of 600 nanometers is much shorter in time than 7 wavelengths out of 1,000 nanometers. So while the width is the same, how far you have to go out is the same in terms of wavelength, but the wavelength is different, right? So since you can fit more wavelengths in the same amount of time, it's like compressing the pulse. And that's the argument. It's like you only have to go out 7 wavelengths, so 7 wavelengths is not as far here than here. So that's why a shorter central wavelength leads to a shorter pulse in time. So those are 2 kind of intuitive picture-based explanations as to why a broader bandwidth leads to shorter pulses and why a shorter central wavelength leads to shorter pulses. But like most of these videos, I usually do 2 explanations. A very intuitive-based one. Here is going to be the calculation-based one. It's more specific. So for the calculation-based explanation, I'm going to use the time bandwidth product. So what is that? Time bandwidth product says that delta omega times delta tau is greater than or equal to a constant. And so what does this mean? Delta omega is the full width half max of the intensity spectrum in angular frequency. So when we've been talking about intensity spectrum so far, we've been talking in wavelength. But if you can convert wavelength over to angular frequency and take the full width half max, that's delta omega. So most of the time we've been talking about delta lambda. This is delta omega, which you can just calculate from the wavelength. So that's delta omega. Delta tau is the pulse duration in time. So how wide is the pulse, right? And then k is just a constant. So if we rearrange this, we get delta tau is greater than or equal to constant divided by delta omega. And so if you think delta omega is the range of my frequencies, is kind of the easy way to say. I mean, you could say it's the full width half max of the intensity spectrum in angular frequency, but that's a mouthful. It's easier to say, okay, it's the range of frequency they have. Do we have a large range of frequencies or do we have one frequency, right? That's what delta omega is. And so why is this true? Why is this equation true? Well, think about it. We just kind of showed that. If you have this picture here. So this is a wave representation with a pulse plotted over it. And we just sort of explained why this is true. If we have a larger range of frequencies, a broader bandwidth leads to shorter pulses, right? A larger delta omega, a larger range of frequencies, if you increase this, delta tau will decrease. We actually just kind of showed why this is true. A broader bandwidth leads to shorter pulses. That's sort of the explanation, right? If you have a larger amount of frequencies contributing to your pulse significantly, these ridges will go farther out and you'll get the cancellation and you'll get shorter pulses. So that's sort of the explanation of why this is true. And this is what I'm going to use to explain calculation-based why broader bandwidth leads to shorter pulses and so on and so forth. So it's going to be a bit of algebra, but we have this intensity spectrum in wavelength here. And what we're going to do is we're going to take the full width half max, and we're going to take the left wavelength and the right wavelength of the full width half max. So if the maximum is 1, 0.5, at what two wavelengths is the intensity 0.5, right? So exactly halfway, what's the width? We're going to call this one lambda 1 and this one lambda 2. Okay? So if we're going to use the time bandwidth product, we need to talk in angular frequency, right? Because it's delta omega, delta angular frequency, times delta tau. So we have to convert these over to angular frequency. So lambda 1 is equal to 2 pi c divided by omega 1, right? That's just easy conversions over to angular frequency. And lambda 2, same thing. So then we can represent this bandwidth, this full width half max, which is delta lambda, which is lambda 2 minus lambda 1. We can just plug these in, right? 2 pi c over omega 2, so on and so forth. Then we can factor out the 2 pi c to get this, right? So now the full width half max is equal to this in terms of angular frequency. Then we're going to do something tricky. We're going to multiply by omega 1, omega 2 divided by omega 1, omega 2, right? This bottom omega 1, omega 2 goes under this entire thing. The top omega 1, omega 2 gets factored into this and cancels out, and we get this. We get delta lambda is 2 pi c times omega 1 minus omega 2, so on and so forth. But notice how omega 1 minus omega 2, that's just delta omega, right? So now we have, this is now delta omega. And so we have this, right? So now we have this. Delta lambda, the full width half max in wavelength, is equal to delta omega. This is good, right? Because we need this for the time bandwidth product, times 2 pi c divided by omega 1, omega 2. So now we're going to make an approximation. And I'm going to go back to kind of explain this approximation. So notice how lambda 2 and lambda 1 are symmetric about the central wavelength. So the central wavelength in this case is 800 nanometers. And since they are symmetric about 800 nanometers, when we convert it over to angular frequency, they're also going to be roughly symmetric about their central angular frequency. Right? So we have this term here, omega 1 times omega 2. And since omega 1 and omega 2 are to the left and right of sort of almost a Gaussian-looking spectrum, we can replace this, we can approximate this with the central angular frequency squared, right? So since they're symmetric about the center, we can just replace this product with the central frequency squared, because one's a little bit lower, one's a little bit higher. We can replace it with the average squared. And so how good is this approximation? Well, if you have if you had a pulse with a 50 nanometer bandwidth centered at 800 nanometers, your delta omega calculated with this formula would be 1.43 times 10 to the 14. And if you did that same calculation with this formula, you get 1.472 times 10 to the 14. That's just a 0.1% difference. So this approximation is pretty strong, and so we're going to go with this one. So if you take this formula and you do some trivial rearrangements, or you start backwards and work your way to this, you get that delta omega is equal to 2 pi c divided by lambda naught squared times delta lambda, okay? That was a lot of algebra, but now we get to use the time bandwidth product, right? And remember the time bandwidth product says that delta tau is greater than or equal to a constant divided by delta omega. Well, now we have a formula for delta omega, which has the bandwidth and the central wavelength incorporated into it, which is nice. So now we can plug this in for delta omega, and we get this. So we get delta tau is greater than or equal to a constant divided by 2 pi c times lambda naught squared divided by delta lambda. But k is a constant, 2, pi, and c are all constants. So we can kind of rewrite this, clean it up by saying k prime is now all of this, right? So it's a new constant. We're just going to call it k prime. Just clean it up a bit. And so now here's our equation, and it's very obvious. If you have a shorter central wavelength, this equation makes sure it's obvious. If you decrease this, you're going to decrease this. If you increase this, you increase the bandwidth, you're going to decrease this, right? So this is a very clear relation. It's interesting that this is actually squared, right? That's something that you wouldn't have seen if you had just went with the intuitive explanation, why this is squared. So it's useful to do calculation-based as well. And so now we have this equation, which is very clear. It's easy to explain. If you have a broader bandwidth, you get shorter pulses. Shorter central wavelength, you decrease this, you decrease this. So now we can go back to our GIFs, and we can kind of plot it again. So here we have our delta lambda and delta omega. And as you can see, as we get a broader bandwidth, we're increasing delta lambda, which increases the denominator in here, which decreases delta tau. And we see that here. The delta tau is increasing as you increase delta omega. So our equation holds. We can do it for the other one too. If in this case we're leaving delta lambda the same, but we're just shifting the central wavelength towards smaller, So that means we're decreasing lambda naught squared, which means we're decreasing the pulse duration, and we see that right here. So a shorter central wavelength does indeed lead to shorter pulses. So there's some limitations to this, right? And this limitations can kind of be shown through the following question. If you were given a fixed central wavelength, can you make arbitrarily short pulses by just increasing the bandwidth? And that's sort of what this implies. If you had an 800 nanometer, let's say we're going to center our pulse at 800 nanometers. In theory, well, not in theory, according to this equation, you should be able to increase your bandwidth as much as you want, and then you can get as short of a pulse as you want. But this isn't true. You can't do this. And this is a fundamental limitation to this, and this is kind of the problem of when you talk in wavelength. So if given an 800 nanometer pulse, can I just get an arbitrary large bandwidth and get a short pulse? And the answer is no. And the way to see this is you have to convert it over to frequency. And the reason you want to talk in frequency is because it's proportional, directly proportional to energy. And so it's kind of nicer to talk like that. So if you convert our intensity spectrum over to, instead of wavelength in terms of frequency, you get a picture like this. So here is a intensity spectrum in terms of frequency instead of wavelength, centered at 800 nanometers. So 800 nanometers converted to frequency is 3.75 times 10 to the 14. So centered at 800 nanometers. So here's our fixed central wavelength. In theory, can we increase the bandwidth as large as we want in order to get shorter pulses? Well, it seems like you can, but notice what happens at zero. If you have zero frequency, that's zero energy. You don't have a photon. You don't have anything. So this provides a fundamental limit, like kind of like a wall that you can't pass, right? Or even approach, really. Because you can't have something with zero frequency, or especially something with negative frequencies, right? So there's a fundamental limit on how wide you can make this. You can't just begin growing this as far as you want because you'll hit zero, and you can't even hit zero, right? So this provides a fundamental limit. So this kind of equation implies that, oh yeah, I can just grow this as much as I want, and you can get arbitrarily short pulses. No, because if you convert it to frequency, you see that you'll hit this limit. And this also provides a limit as how much you can shift. If you wanted to keep the same full width half max and just shift this, you can't shift this however you want. If you shift this too far this way, you're going to get significant amount of waves at zero, which is a fundamental limit. You can't pass this. And so this is sort of the limitations to this equation, but it's still very valid and nice to see that a broader bandwidth leads to shorter pulses and so on and so forth. So that has been video 3. These first 3 videos were all combined. They all had this similar themes. But in the next few videos, I hope to talk more about nonlinear optics. Like I want to make a video on SHG and things like that. But I definitely invite you to watch the other videos. Feel free to share these videos. And I'll see you in the next video. I appreciate the watch. Thank you.